Hi there. In this program, we're going to take a look at energy cycles and heats of combustion. To demonstrate this, let's take a look at this enthalpy cycle we've shown here below. To interpret the data, consider turning W into X. It's an endothermic process requiring 90 kilojoules of energy. To convert Z into X is an exothermic process releasing 60 kilojoules of energy, and similar with the other enthalpy changes shown and their directions. I would like to determine the enthalpy associated with turning W into Z, starting at W, finishing at Z. To do that, I could turn first of all W into X and then X into Z. The enthalpy change to do that, since we're going in the same direction as the original blue arrow, is going to be the same number, 90 kilojoules. However, to go from X to Z, we want to go opposite to the information given in the blue. So I have to reverse the sign. That would be an endothermic process, plus 60 kilojoules. So for the associated enthalpy change, I would simply sum the two together. Is there another way you can get from W to Z? Well, certainly we could do this followed by this. Can you figure out the enthalpy change associated with doing it that way? First of all, we'd have to reverse that minus 140 and make it positive 140, and then add 10. And we can see here, we arrive at the same answer. It's independent of the path. Now, let's look at what's meant by heats of combustion. Some of the key ideas here, it's the enthalpy to burn 1 mole of a substance. And you're going to produce products that are at 298 K and 100 kilopascals. That'll help us with identifying the states of our products. This data is available in Table 14 of your IB data booklet, and I've reproduced a small section of it here. So when I read the first line there, hydrogen's formula H2 gas, and I see the enthalpy of combustion, what that really is the following. Hydrogen plus oxygen making water. Now, I can use fractions here because I'm only allowed to burn 1 mole of the fuel. So the coefficient for the hydrogen must be 1, and the enthalpy change associated with it there, exothermic as we would expect for combustion, negative 186 kilojoules per mole of hydrogen. Let's grab another example from the table. Let's take the bottom one there, ethane. If I was to burn ethane to produce carbon dioxide and water, I would require 7.5 oxygens to do that. And the heat of combustion associated with it would be negative 1,561 kilojoules per mole. So this table has a lot more substances than just these 6. And you can use that to figure out other related reactions. To look at what the products are of combustion, I've got a little summary here. If your fuel or your starting substance has carbon, that'll end up as carbon dioxide. Hydrogen will end up as H2O in a liquid state at 298 K. Nitrogen ends up as nitrogen gas, and sulfur ends up as sulfur dioxide. Now I want to put the two ideas together. I want to figure out the enthalpy change for this reaction, starting here, finishing here, and figuring out the heat here. What I know from combustion data is the heat to burn that particular substance, and I can look it up on Table 14. So the enthalpy change to burn that starting material, C2H2, also called acetylene, is negative 1,301 kilojoules. To burn hydrogen is negative 286. But I have 2 of them there, so I'm going to have to do this twice. The enthalpy also to burn our final product there, C2H6 ethane, is negative 1,651 kilojoules. However, in order to start and finish, I need to reverse that last one. So I'm going to take that arrow away and replace it with this one, but I have to then flip the sign associated with that reaction. So it becomes the negative of negative 1651, or positive 1651 kilojoules. To figure out now the enthalpy change of my reaction, I simply sum up the enthalpy change of all of these steps. In general terms, what we've done is we have the enthalpy of combustion of all of our reactants, and we've subtracted the enthalpy change of our product. This is given in our IB data booklet. The enthalpy change using heats of combustion data is the reactants minus the products. Let's use this equation in an example. I'd like to figure out the enthalpy change associated with the fermentation. And here's the general equation for it. I consult Table 14 in the IB data booklet to get the following heats of combustion. Now I'm going to employ the equation from the IB data booklet. So, first off, I begin with my reactants. I have 1 mole times the heat of combustion for it. That's in the first square bracket. In the second square bracket, I'm subtracting the enthalpy change of those. 2 moles of carbon dioxide at negative 394 each, and 2 moles of ethanol at negative 1367 kilojoules. Adding that up, I get an enthalpy change of 719 kilojoules, an endothermic process. Thanks for watching.